Today, we're going to dive deep into something that sounds simple but is anything but. We're talking about formally verifying a cornerstone calculation of general relativity. And look, this isn't about finding some new groundbreaking physics. It's about the incredible, hidden engineering it takes to prove with absolute, machine-checked certainty what we thought we already knew. Let's get into it. So, what was the task? Well, on the surface, it seems almost like a homework problem for a grad student. You take the classic 100-year-old calculation for Schwarzschild spacetime, from the metric all the way to the Ricci tensor, and you just formally verify it in the Lean 4 proof assistant. It's a foundational exercise, right? Should be straightforward.
Well, not exactly. That straightforward task ended up being a massive engineering project. The result? Over 16,000 lines of code. Now, the number itself isn't really the point, but it's a huge flashing sign that there is a deep, deep complexity here that you just don't see in a pen and paper proof.
And that really brings us to the heart of the matter. Why? Why did this supposedly trivial, well-understood calculation need this much work? The answer, it turns out, reveals this fascinating gap between how we physicists think and reason and what a machine demands for true, verified certainty. Here's how we're going to break it down. We'll start with why this trivial calculation is so tough to formalize. Then we'll look at the actual Lean toolkit that was engineered to solve these problems. After that, we'll uncover the project's real and kind of unexpected reward. And finally, we'll touch on what this all means for the future of physics. All right, let's talk about the formalization gap. This is the core issue. It's this giant chasm between the intuitive, implicit steps a physicist just knows on paper and the brutally explicit, rigorously proven steps a computer absolutely requires. Let's look at exactly what that meant in practice. First up, the index machinery problem. On paper, you write down something like gamma, alpha, mu, nu, and every physicist in the room knows exactly what you mean. There's an implicit summation, you know how the indices behave. But in Lean, that entire concept just doesn't exist. It has to be built from the ground up. We're talking a custom IDX type, functions to handle summation, and a whole suite of lemmas just to prove how those sums can be manipulated. Then you have the side condition problem. In a textbook, you'll see a little aside, right? Oh, and by the way, we're assuming R isn't 2m. You just state it. In Lean, that's a proof obligation. Every single time you divide by something, you have to formally prove the denominator is non-zero. The solution here was to engineer an exterior predicate to bundle all these domain constraints together, and then meticulously thread that proof through every single step of the calculation. This leads to something anyone who's used a prover will recognize: tactic fragility. The first instinct is just to throw the kitchen sink at it, right? Use a powerful tactic like simp and tell it to expand everything. The Riemann tensor, the Christoffel symbols, all of it. And of course, it just timed out. The approach that actually worked was way more surgical. It involved using very targeted rewrite rules on specific lemmas, and then following up with focused tactics like field simp. It's less automated, for sure, but the upside is huge. It's stable and completely predictable. And finally, there's the differentiability overhead. I mean, on paper, taking a derivative is almost a mechanical reflex. You just do it. But in Lean, every single derivative needs a formal proof that the function is actually differentiable at that point. In fact, the project hit a major wall until the C2 smoothness of the metric function was formally proven. It's a huge, often underestimated amount of work. So once all these hurdles were identified, the project's focus really shifted. It wasn't just about getting to the final answer anymore. It was about engineering a robust toolkit to overcome these problems. A toolkit that can now be a stable, reusable foundation for doing more formal relativity. So what's in this toolkit? First, a technique called controlled simplification. Instead of that big, unpredictable automation we talked about, the team used simp only, with very short, explicit lists of lemmas. This makes the proof process not only fast and predictable, but, and this is critical, it makes it stable. It doesn't break when the underlying math library gets updated. The second big breakthrough was a strategy of explicit sum expansion. Instead of letting the prover wrestle with simplifying these complex sums with implicit indices, the team made a decisive move: expand everything first. Expand all the sums into their full concrete forms. This creates a fixed, predictable structure, a normal form that the algebraic tactics can then chew on reliably. And this all culminates in maybe the most elegant solution in the whole project. The Kretschmann scalar, if you just expand it naively, blows up into 256 terms. Proving that simplifies to what it should is a nightmare. The solution wasn't brute force. It was a beautiful structural lemma that exploited the symmetries of the Riemann tensor to prove that the entire 256-term mess collapses into just 6 distinct symmetric blocks. That's what made the final calculation possible. So this brings us to the real payoff of the project. You see, the original goal was actually to hunt for hidden, non-constructive axioms in general relativity. But what they found was something totally different, and you could argue much more important.
The team was using this framework, axiom calibration, to track the logical dependencies. And what you can see here is that the one target they actually formalized, G1, the Schwarzschild vacuum solution, has an axiom profile of 0, 0, 0. It's pure symbolic computation. The really interesting axiomatically rich targets, like the singularity theorems, are still just on paper for now.
So the main discovery was the difficulty itself. The whole point of formalizing this easy case wasn't about finding hidden axioms, because, well, there weren't any to find. The point was discovering the immense engineering that's required to build the foundational toolkit you need to even begin to tackle the hard cases, where those hidden axioms might actually be hiding. So when you look at it that way, the true artifact of this work isn't just one verified result. It's this whole set of reusable tools. It's a reusable tensor calculus library, a concrete benchmark for what it takes to do formal GR, the first real documentation of this formalization gap in physics, and a roadmap for how to tackle the next bigger problems. Okay, finally, let's talk for a minute about how this work got done, because it really points to a new way of doing science. This was a human-AI collaboration from start to finish. And it wasn't just one AI. It was a team of specialized agents. One was focused on implementation and refactoring, another on high-level mathematical strategy, a third provided strategic guidance, and a fourth handled code cleanup. It turns out this kind of specialized collaboration is incredibly effective for managing the sheer volume of detail that formalization demands. But the most important takeaway here is the methodology, this concept of a trust boundary. You treat the AI agents as proposers. They can suggest code, come up with proof strategies, write lemmas. But Lean, the proof assistant, is always the final verifier. Every single line of AI-generated code has to pass the rigorous, formal check of the Lean kernel. That's what makes the result completely trustworthy. The AI suggests, but Lean decides. Look, for 100 years, we've been using computers to automate our calculations. This project is a benchmark for a future where we can start to automate our proofs. So the final question is, what new frontiers are going to open up in physics and math when our reasoning itself can be scaled with the same kind of rigor we currently apply to our numbers? That's something to think about.